Good logic is a way to discipline and refine our thinking. That's why we should all indeed study it. It allows us to spot general forms or patterns of argumentation, and it allows us to do likewise even when it comes to spotting forms or patterns with propositions themselves. Hi, I'm the Amateur Logician from amateurlogician.com. I sincerely hope you're doing well. What we're going to do in this video is to compare basic set theory with propositional logic. Remember, a proposition declares something to be or not to be the case. It's truth functional. It's something that could take on the value of being true or false. It's going to have to take on the value of being true or false, one or the other. And remember, a set, at least roughly speaking, a set is a collection of things or objects. The number of elements or members of any given set can be finite or infinite, or it can be entirely empty. In other words, we can have the empty set. Now, in propositional logic, we have logical connectives or so-called sentential connectives like the and or the or. And these are analogous to set operations like the union between two sets or the intersection between two sets. Moreover, when we think about various logical equivalencies in propositional logic, these are analogous to set identities in set theory. In fact, we can consider propositional equivalencies and set identities as two special cases of Boolean algebra. A long time ago on this very YouTube channel, we talked about how the commutative laws, De Morgan's laws, etc., come in pairs that are duals of each other. And in fact, the same holds true when it comes to set identities in set theory. Consider, for example, the identity laws in propositional logic. We have a pair of equivalencies that are duals, and likewise we have the same kind of thing happening in set theory. In terms of proving a logical equivalency, we can use the truth table, but we can actually do the same thing, basically, in set theory when it comes to set identities and use a so-called membership table. Let's step back. And as I said, notice that we can relate sets in similar ways like we can relate propositions. We can relate propositions with the and sentential connective, the or sentential connective, etc., and we can relate sets with each other with a union or intersection, etc. Now, the union of two sets, let's say set A, set B, the union between them is just going to be equal to X such that X is an element or member of A or X is a member or element of B. And we can visualize this with a Venn diagram. We have a rectangle as a universal set. We have the circle A representing the set A and the circle B representing the set B. We're thinking about anything that belongs to the circle A, the set A, or anything that belongs to the set B, that is to say, the circle B. Consider, for example, set A containing the elements or members 1, 2, 3, and consider set B as containing the elements or members 2, 3, 4. So if we think about A union B, that's just going to be equal to the set A or the set B. So in other words, it's going to contain the members or elements 1, 2, 3, 4. And this is analogous to a disjunction in propositional logic. We can think of P or Q, where we have a disjunction. Or consider the intersection between two sets. So we have A intersection B, and that's going to be equal to X such that X is a member element of A and X is a member element of B. With a Venn diagram, we're only considering the intersection of the two, or in other words, what's the overlap between A and B. So if we consider set A and set B, where set A has the members 1, 2, 3, and set B has the members 2, 3, 4, A intersection B is just going to contain the elements or members 2 and 3, because that's where the overlap is. And in propositional logic, we have something analogous. We can consider the proposition P and Q. We have a conjunction. Next, we can consider the complement. So let's say we have A prime. Another way to write that would be to have A bar. So A prime or A bar is equal to X such that X is not an element or member of A, and X is a member of the universal set. And if we diagram that, not with a Venn diagram, but strictly speaking a Euler diagram, we have A contained in this square, this universal set. We're considering everything outside of A. So that would be our diagram. And in propositional logic, we have something analogous where we can say not P or the complement of P. But what about the proposition if P then Q? Well, that's actually analogous to a subset, interestingly enough. So set A is a subset of set B, where we use this notation. So A is a subset of B if every element of A is also in B. Now set A is a proper subset of B, where we use this notation. So A is a proper subset of B if A is a subset of B and A is unequal to B. So if we diagram that, we can think about A contained within B. Now consider the proposition if P then Q, P arrow Q. P is sufficient for Q, but is not necessarily necessary for Q. Or in other words, we can diagram the situation the following manner. So the big circle is Q, the small circle contained in Q is P. Every time P is true, Q will be true, but it doesn't follow that every time Q is true, that P will be true. So this here, if P then Q, this conditional is analogous to this situation here. So a conditional is analogous to a subset. Moreover, we should note that by definition, for any set A, the empty set is a subset of A, and A is a subset of A. So this right here refers to the empty set that contains no members. And to prove that set A equals set B, we just have to show that A is a subset of B and that B is a subset of A. That is, prove that both are subsets of each other. And that's one way to prove these various set identities. But there's another manner in which we can prove these various set identities, and that is through a so-called membership table. And a membership table is very much like a truth table, which we use in propositional logic. For example, if we look at De Morgan's laws, you see in set theory we have this dual, and in propositional logic we have this dual over here. We can prove both of them with a membership table or a truth table. So let's do that. Let's actually prove this one down here with the so-called membership table. So we're going to prove that A intersection B complement is equal to A complement union B complement. And we will construct a so-called membership table. And it works just like a truth table in propositional logic, really. We'll say A, we'll say B, we'll get A intersection B, we'll get A intersection B complement, we'll get A complement, B complement, and A complement union B complement. And insofar as this, in fact, is equal to this, they will have the same exact values. We're thinking about, are there members contained within the given sets? We'll give it a 1 or a 0, just like we'll give a true or false value to propositions in propositional logic. We're going to say it can be 1, 1, 1, 0, 0, 1, or 0, 0. We have an and. So 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, and 0 and 0 is 0. And then we have a complement. So we'll switch from 1 to 0, 0 to 1, 0 to 1, 0 to 1. We have a complement. So 1 to 0, 1 to 0, 0 to 1, 0 to 1. B complement. 1 to 0, 0 to 1, 1 to 0, 0 to 1. And then we have this or. So 0 or 0, 0, 0 or 1, 1, 1 or 0, 1, 1 or 1, 1. And note that these values here are the same as these values here. So this implies that therefore A intersection B complement, in fact, is equal to A complement union B complement. And we can do something similar in propositional logic to say that P and Q, let's negate that, is logically equivalent to not P or not Q. We can construct a truth table and we'll get a similar result to prove that this also is true. But another way we can prove identities or equivalencies is through a proof where we're resorting to other things already known. So for example, let's say we want to prove that A intersection B union C is equal to A intersection B union A intersection C with a direct proof. We will let X be an element of A intersection B union C. And our goal here, recall, is to prove that both are subsets of each other. So what we're going to do is we're going to prove that this left-hand side is a subset of this right-hand side, and this right-hand side is a subset of this left-hand side. So we're going to do a direct proof. So again, we're letting X be an element of A intersection B union C. If that's the case, then we can say that X is an element of A and X is an element of B union C. Since X is an element of B union C, we know that X is an element of B or X is an element of C. Hence, X is an element of A and X is an element of B, or X is a member or element of A and X is an element or member of C. Therefore, X is an element of A intersection B union A intersection C. So this means that A intersection B union C is a subset of A intersection B union A intersection C. Similarly, we will let X be an element or member of A intersection B union A intersection C. So given that, with a direct proof, then X is an element of A and X is an element of B, or X is an element of A and X is an element of C. We just break this down one by one. Hence, we just walk through this proof. Hence, X is an element of A and X is an element of B, or X is an element of C. Therefore, X is an element of A intersection with the union between B, C, and from that, A intersection B union A intersection C is a subset of A intersection B union C. Conclusion: A intersection B union C is equal to A intersection B union A intersection C. And that concludes that proof, because we prove that both are subsets of each other, so we have a statement of equality. That's a step-by-step proof of the distributive law and set theory. It's explicit in breaking down what it means for X to be a member of the left-hand side and right-hand side, so by double containment, so to speak, we prove that the sets are equal to each other by both being subsets of each other. Now, this is an intro to the fascinating world of set theory and its relationship to propositional logic. Consider giving this video a like, and if you want to support my work, please buy me a cup of coffee. I would appreciate it. Thanks for your viewership, good luck to you, and be well. I'm the Amateur Logician from amateurlogician.com.